So the topic for today is the problem of finding low conductance cuts and a famous result known as the Cheeger inequality. So we will continue this topic for 2 lectures. In the first lecture, that is today, I want to explain what low conductance cuts are, why they're important, and the connection between low conductance cuts and a particular matrix known as the Graph Laplacian, which is a very important topic in a lot of modern graph algorithms and graph theory. There's a discipline called spectral graph theory, which basically studies this problem. So the idea really starts basically with this classic problem of graph partitioning, which is you're given some graph G equals V, and we'll think of this as undirected. And split G into 2 components, removing few edges. So I haven't defined what few edges means. And the process of this discussion is to give you a definition that is very natural for many applications. So why would you want to do this? Well, there are many cases. One, you may want to do divide and conquer. You may want to store the graph in a distributed architecture. You may want to find dense components in G. And of course, this might not find a dense component, but you could recursively repeat it. You would actually see stories of splitting into 2 components for finding dense components. As a classic one is they've taken something like, let's say all the members of Congress, and you put an edge between them if, let's say, they tend to vote on similar issues, if they vote the same on similar issues, and then you go ahead and split into 2 components, and of course, not surprisingly, you will get the Republicans and the Democrats sort of well clustered. And this sort of experiment has been done in many, many situations. And so this question comes up as you want to split the graph into, again, we'll just start with 2 components, removing few edges. And the question is, how does one frame this formally? So you might say, why not min cut? We know how to solve min cut in polynomial time. So we could just go ahead and compute the min cut, the global min cut. And the problem, if you think about it, if G is sparse, then the min cut might be just the lowest degree. Indeed, we know that the min cut is going to be at most the lowest degree. And so in all cases, so if you have a graph where, let's say, there's a vertex of degree 3, well, then that vertex is going to, the 3 edges over here would give you a min cut because it separates the graph into 2 connected components, removing the fewest number of edges. The problem is you want to split into components of comparable size. We want the components to not be very large. The whole point of divide and conquer is to break it up into 2 maybe equal or at least somewhat balanced portions. And so a natural way of looking at this is to say, let us find a set that minimizes the boundary to size ratio. And so when we start formalizing this, this is actually referred to in actually coming from classic Greek geometry is what is known as the isoperimetric problem. And so the isoperimetric problem was actually formulated first in 2 dimensions, but you can ask, what is the shape, the closed shape of unit area with the minimum perimeter? So does anyone know what the answer is? So what is the closed shape of unit area with the smallest perimeter? Any guesses? What is the most, what would be your obvious guess? A square, a triangle?
A circle?
A circle, exactly. The proof is non-trivial. It was actually proven, I think officially proven 2,000 years after it was first posed. It was posed by the ancient Greek geometers and they guessed the answer. But the proof required more mathematics. So why am I bringing in isoperimetry? You can think of this as size, and you can think of this as boundary. So you can think of this as the volume and think of this as the boundary. And in general, you can prove this in any dimension where you replace area by volume and perimeter by surface area, and you get the circle. Now one can ask the isoperimetric question, the isoperimetric problem on a graph. So we'll define the boundary. The boundary of a set, I will say, is the number of edges that cross the set. You can also look at the vertex boundary. This is specifically the edge boundary. So I'm actually talking about the edge isoperimetric problem. So this is the boundary. Define the volume, which is called the volume of the set, to be the sum of degrees. So the volume of this is just the total number of edges. And the boundary is the number of edges crossing the cut. And what we can think of is, in some sense, the isoperimetric value of S. So this is actually going to be our first guess. This definition is going to have a flaw, but we can say the isoperimetric value of S is going to be del S, the boundary size, divided by the volume. And one can ask, okay, can we find, in a specific graph, find the set that minimizes the isoperimetric value? Unfortunately, as defined, there is a trivial answer to this question. So what is the trivial answer that minimizes this quantity? Think of a set that minimizes the numerator and maximizes the denominator. What is a set that minimizes this quantity? Trivial. Note that it's not a singleton, the isoperimetric value is 1. Note that the isoperimetric value is always at most 1.
So you pick the biggest degree vertex?
But a single vertex will always have value 1.
But the volume as you defined it is the degree of the vertex then, right?
Right, but then the boundary is also going to be...
Oh, the boundary is also increasing, right?
Yeah, but okay, so how would you get... Okay, so give me a set whose boundary is 0. What is a set whose boundary is 0?
The entire graph.
The entire graph, exactly. So if you took the entire graph over here, note that the isoperimetric value is 0. Right, so the problem with this definition, this is important to understand so that when I give you the actual definition, it won't look mysterious. There's a problem. And the problem is that for S is equal to V, the entire set, the isoperimetric value of S is equal to 0. So that's the trivial minimizer. And in some sense, we have a problem here because if you take a set that is extremely large, even though there are a few edges that are going out, the volume is going to be very large. And you have a similar problem here. Indeed, this is starting to look a bit like min-cut now because essentially this is biasing towards large sets. We want S and S complement to be balanced. So a fix for this is to define phi of S. This is the conductance of S, and this is going to be our isoperimetric value. So we are going to define the conductance of S to be the boundary divided by the min of the volume and the volume of the complement. Right, so in this case, what would happen is that the volume of the complement is extremely small and therefore the conductance will go up. Note that the way this is defined, phi of S complement is equal to phi of S, so I will just use the complement notation. And this is called the conductance of S. There is another quantity referred to as the sparsity of S. So this we will also see. So this is the sparsity of S. And this is defined by looking at the volume of S times the volume of S complement, but we do a normalization here. So we'll actually multiply this by 2 times m, and 2 times m is equal to the sum of all degrees, which is the total volume. The conductance and the sparsity are essentially related to each other. And they're related to each other exactly by a factor of 2. Okay? And you'll see, in some notes, they actually flip these notions. This is called the sparsity, this is called the conductance, and the first one is called the sparsity. It doesn't matter because we will be ignoring constant factors anyway. So as an exercise, what you can see is that alpha S is at least phi times S and at most 2 times phi of S. Actually, I hope I haven't flipped these. So maybe let's just verify that. So observe that when these are equal, then this is going to be essentially twice the conductance. So I think I'm sorry, I've switched it. Is it most 2 times alpha s? Alpha s. Okay, right. So the conductance and the sparsity are they're basically a 2-factor within each other, and we will be switching back and forth between them depending on which is convenient. So sometimes you'll refer to what is called the sparsest cut or the minimum conductance cut. So the conductance of the graph, this is the conductance of the graph, and this we will define as the minimum over all sets S of the conductance of the set. And similarly, you can define the sparsity of the graph in the same way, and the minimizer is the minimum conductance cut. So the way that, and this is extremely common in many different fields, is when you want to split a graph into 2 parts, you find the min conductance cut. And that will usually, that won't always split into equal parts, but usually will be biased towards that. So if you look at something like image segmentation, in image segmentation, conductance plays a strong role. If you look at social network analysis, people use min conductance cuts, not to split into 2 parts, but usually to find cuts of low conductance. If you look at even like distributed algorithms, and when people are taking a graph and they want to partition it into pieces that can be kept, they will sometimes use minimum conductance cuts. Indeed, even if you're looking at a linear system and you want to solve a linear system, they will construct a graph based on the variables, the matrix of the linear system, find min conductance cuts from there, and then use it to partition. So this appears in many different places, and the question is, it turns out this is, computing the min conductance cut, this is a hard problem. So computing the conductance is, depending on how you phrase it, it would either be NP or it would be co-NP hard, or it's typically a hard problem. And I say co-NP because, depending on, depending on whether you phrase it one way or the other, it could be NP hard or co-NP hard. But I'll just say that in general, computing the conductance is hard. And so, but how to compute approximations of the conductance. And this is what this lecture and the next lecture are about. And so we'll begin in our usual setting by, let us write an integer. Now it turns out the program is not going to be linear. It's going to be, I say an optimization program because it's actually going to be a quadratic program. But in the vein that we have discussed before, so let's just start. Let's say X is an indicator for S. Right? So X is basically some element of 0, 1 to the n. So let X be an indicator for S. We're going to write technically the sparsity in terms of a program, in terms of an integer program, and then we will talk about relaxations of that program. Okay, so think of it, here is some potential cut. And this is S. So we put zeros here and we put ones over here. So the boundary is the number of edges that go across. Now technically we don't know which one is 0 and which one is 1. So what we could write is that the boundary of S is the summation of all edges uv of xu minus xv squared. Right? Because whenever the edges are on opposite sides, you get a 1, and otherwise you get a 0. So you have some quadratic form that represents the size of the set. Now let's look at the volume of S times the volume of S complement. So we can write this as summation over all vertices of xv times dv times the summation over all vertices of 1 minus xv dv. Right? So this would be the volume of the set, and the latter would be the volume of the complement. So let me expand this out a bit. So just by looking at the product, I can look at all uv in v cross v. So they're not edges, but just all pairs. I'll get xu times 1 minus xv du and dv. All right? So what I get is 1 minus xu times 1 minus xv du dv. So let's observe something here, that if xu is equal to xv, then xu times 1 minus xv is equal to 0. If xu is not equal to xv, then 1 of xu 1 minus xv or xv 1 minus xu is non-zero. Actually, exactly 1. Right? Exactly one of them is going to be non-zero. So if they have the same value, then either xu is 0, in which case we're done, and if xv is 1, then we're also done. In this case, one of them is 0 and one of them is 1, in which case if xu is 0 and xv is 1, then this one is non-zero, and vice versa. So exactly one of them is non-zero. So if you look at this term over here, I can rewrite this as saying I look at the sum over all uv in v transpose v. And again, I can encode equality by taking the square again. Now, technically, in this I double count, so I'm going to put a half over there. Right? I double count, so I put a half. Does that make sense? Questions? Okay.
I don't think I fully follow the last step.
This step over here, or you mean this
Yeah.
step? Okay. So I'm just saying that look at this term over here. So I'm just looking at this one, this term over here, right? So do you see that when xu is equal to xv, then this is 0?
Yeah.
So if xu is not equal to xv, let's look at the terms for xu and xv. And they're going to be, it's going to appear 2 times. It's going to appear as xv times 1 minus xv, and you'll get xv times 1 minus xu. Like you're going to get both of these terms in this with u and v swapped. One of those is going to be 0 and the other one is going to be non-zero.
I see, but how are you going to deal with the du and dv?
I'm sorry. My apologies. There. Sorry about that. Yes. Yeah, so it's just you have to multiply with the du dv. Yes. Okay, so sorry, does this resolve that now?
Yeah.
Yeah. Yeah. Okay. So any other questions about this? Okay. So let's go back to the sparsity definition here. So remember we said the sparsity is del S is going to be the numerator. The denominator is going to be the volume S times the volume of the complement. This is where taking the product of the volumes was more convenient than the min. But you could use the min and you can sort of apply some sort of similar argument here. So if we take this 2m times summation of xu minus xv squared over all edges divided by, so we have a half over here, the summation of all uv in v cross v, xu minus xv squared du dv, and then we can minimize this over all x which are in 0, 1 to the n. And this is exactly the conductance of the graph. So I'm going to state this as a lemma, which we just proved. So this gives us our optimization program, although it's a very strange optimization program because it has something in the numerator, it has something in the denominator. It's not clear exactly how we're going to process this or even make sense of this. But we now have an optimization program that we can state. We have this optimization program. This is, as stated, this would technically be the sparsity of G. Technically be the sparsity of G. Okay? All right. So let's focus. So I'm going to ignore the 2 factor. The 2 factor didn't come out here, right? It's just a constant. I'm going to keep the 2m lying around because you'll see that that is going to be that's going to be convenient to keep around. So let's focus on this again. Xu minus xv squared uv in E divided by the sum over uv in v cross v of xu minus xv squared du dv. So this seems like a very strange, how does one make sense of this? So let's observe that suppose the graph was a clique, right? So v cross v is basically E, right? Except, okay, so there may be a factor of 2, but v cross v is E. And du and dv would be the same. They would be n, and m would be n squared. So when the graph is a clique, this is just a constant.
Sorry, why does it v cross v is E? I don't get it.
Oh, when the graph is a clique. Suppose the graph was a clique. Well, then all edges are present, right? So all pairs. Okay, so when u is equal to v, then you can ignore this term because it's going to be 0 anyway. When the graph is a clique, the edge set is exactly v cross v. Right? Double counted. So the way to look at this is if your graph looks something like this, but there are lots of edges in here, then you could set 1s to everything here and 0s to everything here and get this quadratic you can get this quantity to be quite small because you only pay xu minus xv for these edges, whereas you have to pay xu minus xv in the denominator for all pairs. So the denominator is going to go up and the numerator is going to be quite small. This is just restating what we had, but I just want to sort of show you the intuition behind this math over here. Now, when we have a quadratic, it's useful to write in matrix notation. And what do I mean by that? And especially if you have a homogeneous. So these are all homogeneous, right? Because the degrees of all terms are 2 with respect to x, thinking of x as the variables. So it's useful to write this in matrix notation. And so what is the matrix notation? Well, you can always write a quadratic form. So if you have this quadratic polynomial f of x, homogeneous quadratic polynomial f of x, you can write this as x transpose mx for some matrix m. Again, just so that you see this exactly. So this is x transpose. This is m. And this is x. And if you look at what this quantity is, this is exactly the sum over all I and j of mij xi times xj. Right? So the coefficients of the quadratic are exactly the entries of the matrix. And you have an equivalence. Right? You can take any quadratic and you can write it in this form. And of course, the ijth term will appear twice. Right? It'll appear as mij and mji, and you can just split it in half. So you can basically convert the quadratic into a matrix form and something that looks like x transpose mx, and you can convert x transpose mx into the quadratic form. Now this is going to have a very specific name. This is called a Rayleigh quotient. So the point is, we can write our numerator and denominator in terms of Rayleigh quotients. And when we write it in this form, we will get some insight into an algorithm to actually compute the conductance, or at least get some to estimate the conductance. Okay, so I want to look at this quadratic form, and this is very special. So this is summing over all edges of xu square, xu minus xv square. So I can just expand it out. So I sum over all edges of xu square plus xv square minus 2xu xv. Okay, so fix a u. Fix a vertex u. How many times does it appear in this form? If you were to fix a u, how many times does xu square appear?
Degree of u times.
Degree of u times. So we can write this out as the summation over or u or v. So you sum over all vertices, you get xv squared times the degree of v minus 2 times the summation of xu xv for uv as an edge. Right, this is just what you get as a quadratic form. Now this is really nice because we have a very nice matrix way of writing this. Okay, and what we can write is x transpose dx minus x transpose AX. Okay, what is D? This is the degree matrix. And this is simply, so we will think of the rows and columns indexed by vertices. So this is just going to be the degree of U. So I'll think of this as U and V. So if U is equal to V, and if U is not equal to V, this is 0. So this is a diagonal matrix. It is a diagonal matrix where what you have here is simply the degree. Degree 1, degree 2, up to degree n. That's what this matrix is. That's D. A is just the adjacency matrix. A is just the adjacency matrix. So I can actually write this as X transpose D minus A X. And D minus A has a very special name. This is referred to as L. And this is called the Graph Laplacian. Why is it the Laplacian? It's actually this quadratic form. So I said that whenever you have a homogeneous quadratic, you can always write it as X transpose MX. This specific quadratic, and actually you can write it as a symmetric, and M is going to be symmetric here. I should have said that M is symmetric. So what you have is the graph Laplacian, which is a symmetric matrix. So the numerator we can write as X transpose LX, which is just equal to XU minus XV squared. There is something else to be noted here, that for all vectors X, for all X in Rn, X transpose Lx is greater than or equal to 0. So L is also called positive semi-definite. And this is equivalent to saying that all eigenvalues are non-negative. So the graph Laplacian, or rather this X transpose Lx, is precisely the numerator for the sparsest cut quadratic program. It's a quadratic integer program. In that quadratic integer program, the numerator is exactly a Rayleigh quotient of the graph Laplacian. And it's called Laplacian because this quadratic form, xu minus xv squared, comes up in the heat equation. So this is when you draw connections to physics, and if you're trying to understand how heat moves through a surface, just take a two-dimensional grid, a two-dimensional surface, and how heat dissipates. And this quadratic form comes up basically in the differential equations. And so it is referred to as the graph Laplacian. So this is a very important matrix. It is positive semi-definite. All eigenvalues are non-negative. Moreover, the all ones vector, which I will often denote as follows. The all ones vector is an eigenvalue, is an eigenvector of eigenvalue 0. It's easy. You plug it in over here and you see that you get 0. Right? Basically, this is just saying that 1 transpose L1 is equal to 0. Right? Or L1 is just equal to 0. When you apply the Laplacian on the all ones vector, or actually any vector where all coordinates are equal, then you get a 0. And I won't get into this, but in spectral graph theory, you can look these things up, that if the eigenvalue 0 has higher multiplicity, then that implies connected components, or actually the multiplicity of the eigenvalue 0 is exactly the number of connected components in the graph. But let's not get into that. So anyway, so this gives us the numerator, X transpose Lx. Okay? Any questions about that? So we've parsed the numerator. Now let's go ahead and parse the denominator, which is going to be somewhat, it's going to be somewhat more, it's a little bit, okay, let me write it out and then we can discuss it. So the denominator was the summation of u, v, and v cross v, xu minus xv squared, du, dv. Okay, so let's write this out again. So we'll do the same thing, summation uv and v cross v, du dv of xu squared plus xv squared minus 2 xu xv. Okay, and then let me now do some more expansions. So let me now fix the, make sure I'm doing this correct. So let me fix a u and then sum over all v. So I'll fix u and I'll sum over all v. So if I fix u, so I can, let me first do this. So I fix a u, and then I will sum over all the v's. So I'll get du, and then I can sum over all v's. And what I will get over here is I'll get dv. So let me make sure I'm doing this correctly. Xu squared plus xv squared minus 2 xu xv. So I just want to make sure that I write this in the most convenient way for us. So I'll sum over all the vertices. So what I can do is if I fix, okay, so let me, I think it's going to be convenient for me to split these terms apart so that we can discuss them separately. So we have summation of uv of du dv xu squared. And note that this is going to be multiplied by a factor of 2, right? Because the xv and xu they're basically symmetric. And then I get this additional term of minus 2 uv in v cross v of du dv xu xv. Right? Du dv xu xv. So sorry, let me ignore this thing that I wrote here. So now let me look at that quantity here. So I get a 2. Now if I sum over u, so I get du xu squared, then I get a sum over all v. Right? The v part comes out. This quantity here, it's uv du dv xu xv, and this is basically just, it's a Cartesian product. So I can simply write this as summation of du xu squared. Okay, so when I expand this out, now this is just 2 times m. So when I do these manipulations, I get 4 times m over here, summation of, I'll just sum over v, dv xv squared minus 2 summation over all vertices v dv xv, and the whole thing squared. Okay, so are there any questions about this point? Okay, I'm going to simplify this further by one more step. If I look at this, you can see that this is exactly the quadratic form x transpose dx minus 2 times, I'm going to write something here, d dot product x square, where this is actually the vector of degrees. Right, so instead of the diagonal matrix, I just look at the vector. I can also look at this as Rayleigh quotient, but you know, it's going to be the same thing. So, or I can, if I wrote this as a Rayleigh quotient, it would be the vector 1 times dx. It's the sum of entries in dx, which I'll write also as follows. So this is the denominator, and what we had above was the numerator. So I'm just going to put it all together so that we can see this in its full glory. So remember that what we had was this quantity here, right? 2 times m, which we wrote as 2 times m x transpose Lx divided by 4 times m x transpose dx minus 2 times dx squared. Okay, and we just said that this is just equal to 2 times m uv and e xu minus xv squared divided by the summation of uv in v cross v xu minus xv squared du dv. This equivalence here had nothing to do with the fact that it was binary. Okay, so our original program said alpha g, or 2 times alpha g, is equal to the min over all x in 0, 1 to the n of 2 times, of this thing here. The relaxation that we're going to take is we're just going to replace this with all reals. All reals. So what we get is 2 times alpha g is at least the min over all x in Rn of the same quantity. Of the same quantity. And just by this equivalence, it's going to be convenient for me to write this. I'm just going to write this as the min of x in Rn of 2 times m x transpose Lx divided by 4 times m x transpose dx minus 2 dx squared. Okay, so this is the relaxation. This was the program, this is the relaxation. Now you might say, this is such a strange thing. How do you know you can even compute this? For linear programs, we were able to compute the relaxation. What I'm going to show you is that this here is an eigenvalue problem in disguise, and eigenvalues can be computed efficiently. Now this is not obvious, but this is going to be an eigenvalue problem in disguise. And it's disguised fairly well because it's hard to pull out. It's an eigenvalue of a particular matrix, not of the Laplacian, but of a particular matrix called the normalized Laplacian, which we will have to study. But this gives a relaxation. So this only gives one side. This only says that the conductance is at least something. The at most is what the Cheeger inequality gives you. Any questions up to this point? I'll pause here and I'll take any questions that you have, because then we'll dig into seeing how this is an eigenvalue problem. Just pause the recording here. Okay, so let's continue. Now let's see why this is an eigenvalue problem. Okay, let's kind of dig into that. So we want to solve this minimum over here. Now, this term is annoying. This term is really annoying. It would be nice if we could get rid of it. And what we'll do is we'll actually just go ahead and get rid of it. And how? So observe the original program here. Observe the original program over here. Note that, okay, so I'm going to write this program, and, for convenience, let me just refer to this as f of x. So just some function, the entire thing. The entire thing is just going to be f of x. Okay? So I'm going to state a small claim here, is that for all constants, f of x is equal to f of x plus 1 times c. Meaning that if I were, so think of it as, this is x, which you think of as a vector, and this is like the all ones direction. If I move x along the all ones direction, the value does not change. That's because this function only depends on the differences of values, and the differences won't change. Right? And the proof is because f only depends on differences between x coordinates. Okay? Now this is going to be convenient.
Sash,
Yes?
C is a scalar, right?
It's a scalar. Oh, I'm sorry. C is a scalar. C is a scalar, not dot product. You're right. C is a scalar. Right? So this is x plus 1 c. So maybe I should write this as c times 1. It's a scalar. So it means I can shift along the scalar and it doesn't change the value. The reason for this is I can now choose my x in such a way that this quantity becomes 0. So what I will do is choose c so that x plus c1 dot product with d, the degree vector, is 0. And indeed the choice is quite obvious, right? Basically because you can look at that, it's basically x dot d plus c times 2m is 0. So you just set c to be equal to minus 2m divided by d dot x unless it was already 0. So what this means is we can assume that x dot d is equal to 0. We can just assume that it's going to be equal to 0. And this is now going to be immensely convenient for us because I can change the problem now. The relaxation is now going to be the min excuse me, over all x in Rn such that x dot d is equal to 0. of something that looks now much more nicer, x transpose Lx, which is what I get in the numerator, and the denominator is just x transpose dx. And the m will also cancel out, so I get x transpose Lx divided by 2 times x transpose dx. So this is now a significantly more convenient form for me to use. Again, of course, it's still not clear how one would solve this. It's still not clear. But now we're going to start seeing connections to eigenvalue problems. So this is now our relaxation, right? So what we again get is that this is at most 2 times alpha g. And I'm going to sort of remove this from here and put that there to get 4 times alpha g. Okay? Any questions about this?
So I think there's a typo in C. It should be d times x.
I'm sorry,
over
you're right.
2m.
You're right. D times x divided by 2m minus of that. You're right, exactly. Yep. Yeah, C is the reciprocal of that, yes. Which makes sense, right? So because if d times x is 0, then C is equal to 0. Sorry, yeah, I thought there was something off there. Okay. So this is our relaxation now. So you are minimizing. So the way to think of this geometrically, is that x dot d equals 0 is sort of some hyperplane. And you're looking at the points in the hyperplane and you are minimizing this quantity over the hyperplane. Now it's a ratio, which is really strange, right? And that becomes one of the challenges in actually showing the Cheeger inequality, which you're dealing with ratios. But what we'll see is that this denominator is like a normalization. Okay, so let's investigate. We want to write this in a more convenient form. Excuse me. We want to write this in a more convenient form. So x transpose dx is just the sum over all vertices of xv square dv. This looks a lot like a Euclidean norm. If dv was all the same, if all the degrees were the same, this would just be a Euclidean norm. Unfortunately, all the dv's are not the same, so it's not a Euclidean norm. But this is like a scaled Euclidean norm. So I'm going to write this out over here as follows. Okay, so I can write x transpose dx. I'll show you this in multiple ways. So you can write it as xv root dv squared. And then this starts looking like a Euclidean norm. Equivalently, I can write this as x d to the half x transpose d to the half x, where d to the half is simply the matrix where I have the root of degrees. It's just the diagonal matrix. It's the square root, right? And so x transpose dx is the Euclidean norm squared. So what this suggests is that the right view is we should just scale the coordinates, because if we scale all the coordinates by root d, then things are going to be more convenient to look at. So let's just set vector v. Let's define, y. So y is in Rn such that yv is just going to be root dv xv, or in matrix notation, y is just going to be equal to this matrix vector product. And then the numerator, the denominator, just becomes, this is just equal to the Euclidean norm of y squared. Now let's look at what this condition means. Let's look at what this condition means. So we said dx is equal to 0. And this is equivalent to saying that this is equal to 0, right? Because 1 transpose times this is just going to be the sum of all entries. And we can write x is the same thing as t to the minus half of y. And so if we plug this in over here, we get 1 transpose d half of y is equal to 0. Right? This is just the equivalently, again, I'm just writing this in many different ways so that you see it. D times x is 0 simply means that summation of dv xv is equal to 0. I can write that as just the summation of root dv yv is equal to 0. So I replace the condition, replace dx equal to 0 with so I'm just going to abuse notation. I'll just say this is like the vector of square roots, right? This is the vector of square roots dot y is equal to 0. So in this, I've shown you that you can replace this by just saying x y dot the root degree vector is 0. I've shown you that the denominator can be replaced by a Euclidean norm. Now let's look at the numerator. So x transpose Lx is equal to, we can replace it x with this quantity here. So we get d to the minus half y transpose L d to the minus half y. When you put this all together, you get y transpose of this matrix. And the transpose of this matrix is just itself. T to the minus half L t to the minus half of y. This is called the normalized Laplacian. This is a normalized matrix, and this is an important matrix for us to understand. So I'm going to just write out what this matrix is. D to the minus half, remember the Laplacian was d minus a. So this just gives identity minus d to the half a minus d to the half. The normalized Laplacian is also given this name, n. So what is nuv? Just convenient to write this out so that we see what's going on here. So if u is equal to v, then it's 1. If uv is an edge, because that's when you get the adjacency, you have minus 1 divided by root du dv, and it's 0 otherwise. This matrix is called the normalized Laplacian. This matrix is the normalized Laplacian. Okay, before we get into the normalized Laplacian, I want to go back and I want to write down all the conditions that we have over here. So the relaxation now becomes the min over all vectors y in Rn such that y dot root t is 0 of y transpose n y, the normalized Laplacian, divided by the Euclidean norm squared. But this is excellent because now what you can do is, this is just a normalization. This is exactly a normalization because I can write y transpose n y divided by the Euclidean norm squared as simply y divided by the Euclidean norm transpose n y divided by the Euclidean norm. So what this beautifully works out to be is just saying that this is just some unit vector. I should say unit norm vector. It's just a unit norm vector. So let's just replace this. Abusing notation, I'm just going to use y again. I'll say y is in Rn. Y dot root d is equal to 0. And the Euclidean norm is equal to 1. Because I can just normalize of y transpose n y. And so this gives our relaxation. So we get, I believe I got, was it 4 times that or 2 times that? I think I'm missing the constant here. Anyway, so I think it was 4 times the sparsity is at least this. Okay, so far so good. Okay, any questions at this point? Okay, now we're in business. Now actually this condition is going to be very interesting. So remember that d minus a of the all ones vector was 0. So that also means that if I do the normalization, right, I can basically do the normalization here. So if I were to write, so here's one way of writing this. If I take d minus a minus root t to the minus half t to the half 1 is equal to 0. Right? And I can basically put a d to the minus half here. And so what I get is, essentially the implication I get is n times t to the half times 1 is equal to 0. This is just exactly the degree vector with square roots. This is equal to 0. So this vector is an eigenvector. It's an eigenvector of n. It's an eigenvector of n with eigenvalue 0. Right? So this is saying, now let's just restate the relaxation. What is the relaxation saying? It says, find a unit norm vector that is orthogonal, to the eigenvector of smallest eigenvalue. why the smallest eigenvalue is 0. Because we argued, remember we said that the matrix L is positive semi-definite, and when you multiply on the sides as well, it still remains positive semi-definite. So all the eigenvalues are non-negative. There's one eigenvalue, there's one eigenvalue 0, which is the minimum eigenvalue. And so we're finding a unit norm vector that is orthogonal to the eigenvector of the smallest eigenvalue, such that, so find a unit norm vector y, such that the Rayleigh quotient of y is minimum. Right? That's what this program is saying. Like once you do all these manipulations, you're saying find a unit norm vector that is orthogonal to the unit vector of smallest eigenvalue, such that the Rayleigh quotient is minimum. And this, so what is this quantity? What is this? What is y, and what is the y that does this minimization? And what is the Rayleigh quotient going to be?
It's the largest eigenvalue of the graph of the Laplacian.
No, it's going to, you're minimizing.
Oh.
But you're on the right track. It's the smallest. It's the second smallest, because the smallest one is 0. And this is precisely the second and by second I mean the second. So the largest is usually would be of right, so I'll just is the second smallest eigenvalue of n, this meaning that the Rayleigh quotient is that and y is the corresponding eigenvector. So I'll explain this shortly. So, but let me just say the relaxation, just to write this out, and this is again, state this as a theorem, is that for alpha g is greater than equal to the min of y in Rn, y dot this vector is 0, the unit norm 1, y transpose ny, which is equal to lambda 2, where lambda 2 is the second eigenvalue. Okay, this is the relaxation. So this is actually the easy side of Cheeger, which says that the second eigenvalue of the normalized Laplacian is a lower bound on the sparsity up to this constant 4. But let me explain this. Yeah.
So I might be getting a bit ahead, but it just struck me. So the Courant-Fisher theorem is actually the von Neumann theorem version with this.
Von
the
Neumann.
minimax theorem of the so Courant-Fisher theorem is
yeah. So this is a consequence of Courant-Fisher.
Yeah, but like, does that come out of the same, like, come out of this program the same way the von Neumann minimax theorem?
No. Von Neumann duality is something different. That's very different. The Courant-Fisher, I will actually show you. I mean, I'm not going to prove Courant-Fisher explicitly, but I'll show you how Courant-Fisher comes by. So this is, you're right that this comes from the Courant-Fisher minimax principle. This comes from Courant-Fisher, but let me explain why this is the case. So let's look at n. Right? So n is symmetric. Positive semi-definite matrix. Now, because it's symmetric, it has n eigenvalues and real eigenvalues, and those eigenvalues I'm going to write down are lambda 1, which is 0, less than equal to lambda 2, less than equal to lambda 3, up to lambda n. Remember, the first eigenvalue is 0. And we just discussed this because that's this calculation that we did here. The first eigenvalue is 0. The second eigenvalue is the relaxation. And there are corresponding eigenvectors. So the first eigenvector, and I'll use u1, u2 to un, u1, u2 to un, and u1 was basically it's this vector. I mean, it's suitably normalized, normalized by this vector, normalized so it's unit norm. So you have these corresponding eigenvectors which form an orthonormal basis. So whenever you're dealing with matrices which are symmetric and have this nice structure, you look at the orthonormal basis, you write everything in the orthonormal basis. So any vector y can be written as summation alpha I ui. And if it's unit norm, then it can be written as this, where the summation of alpha I squared is equal to 1. Right? So I, or maybe I should say, yeah, so I'll use I over here. So I is going from 1 to n. And I'll just so that we distinguish vectors and scalars, right? So any vector can be written in this orthonormal basis as so. What is the Rayleigh quotient? So the Rayleigh quotient which is y transpose n y, you can see is essentially what is n times y in the eigenbasis. Well, that's very easy to determine. It's just going to be, you're going to multiply all of these by n. Okay, so maybe I should write this out here. Let me write this out as, let's just look at what n times y is. So this is sort of standard linear algebra. N times y is going to be alpha I ui, I going from 1 to n. So I write this out, n times 1i, and I alpha I n times ui. So what is n times ui? What is n times ui? Ui is an eigenvector. So what is n times ui?
Corresponding eigenvalue
Is
times ui.
Which is lambda I, exactly, right? So I get alpha I lambda I ui. That's what n times y is. What is y transpose ny? Well, y transpose ny is basically the summation I going from 1 to n alpha I ui dot product, because it's just transpose, dot product with the summation of I going from 1 to n alpha I lambda I ui. But this is an orthonormal basis, right? So dot products are very easy to take, right? You can just multiply the corresponding coordinates together, and so what you get is this quantity, right? Summation of 1 to n alpha I square lambda I. And you know that the summation of alpha I square is equal to 1. Now if let's go back and look at our program here. And I'll tell you why you get the second eigenvalue. You can use Courant-Fisher, but this is I'm basically doing a stripped down, simplified version of Courant-Fisher for this setting. You want to minimize this quantity. You want to minimize the Rayleigh quotient, subject to the norm being 1. So you're subject to this condition. You're also subjecting to this other condition here, which is y times root t is equal to 0. Now, what does that mean? Lambda 1 was equal to 0. And alpha 1 is also equal to 0 because alpha 1 is precisely, if you look at, okay, so maybe I should write this out over here. Alpha I is precisely y dot ui. Right? I mean, this is an orthonormal basis, so it's the dot product. And so you know that alpha 1 is equal to y dot this root t vector, which is 0. So what you really have over here is I going from 2 to n, alpha I square lambda I, subject to summation alpha I square being 1. How do you maximize this quantity? Well, you put all the alphas onto the largest value here, right? So if you want to minimize this, subject to this, where I is going from 2 to n. This is precisely the program. The solution is quite easy. Solution is set alpha 2 is equal to 1, meaning y will just be equal to u2. And y transpose ny is just going to be lambda 2. That's the solution based on this analysis, right? So, for the comment on Courant-Fisher, yes, you get it by Courant-Fisher, but you can also directly prove this. This is precisely the definition. You can think of this as the definition of the eigenvalue. The eigenvalue is precisely the minimum of this quantity. And one can look at this by looking at the Rayleigh quotients. Generally, you need to do more complicated things when n is not symmetric, it's not well behaved, then you have issues. But when n is Hermitian, everything is nice. And we are dealing with a symmetric positive semi-definite matrix, which is like the best kind of matrix one could hope for, in which case all the math becomes really simple because the eigenvectors form an orthonormal basis. All the eigenvalues are real. In this case, they're all non-negative. And so this piece of math becomes quite simple.
There is no utility to the normalization apart from bounding the eigenvalues by a constant, right?
Which normalization? You mean this normalization?
The Graph Laplacian.
You mean looking at the normalization of the Laplacian, you mean?
Yeah. Like, I'm trying to, so, as I see it, this only helps me because it gives me eigenvalues between 0 and 2.
No, it's actually more than that. Actually, it turns out that if you don't do the normalization, it doesn't look like an eigenvalue problem it's not an eigenvalue problem. So let me maybe see here is the relaxation as before without the normalization. This is not an eigenvalue problem until you do this thing where each of the you have to rescale the coordinates to get an eigenvalue problem. So it's deeper than that.
Nice.
This is telling you that the right rescaling is given by D, by splitting D into root D and root T, because that happens to make this a Euclidean norm. That's one way of looking at it. You can think of this is like the denominator is a scaled Euclidean norm. And hence this is an eigenvalue problem in the scaled space. And you do the scaling, but it's only an eigenvector of the scaled matrix. And the scaled matrix behaves differently from the Laplacian. The normalized Laplacian and the Laplacian actually have different behavior.
That's a little funny, right? Because...
Well, I mean, not different behavior is in the... No, let me restate that. I'm sorry. They have... No, sorry, I misspoke. They have the same behavior, but there's a scaling involved.
The scaling isn't like a simple scalar scaling.
No. It's think of it as each coordinate has been stretched out.
So is there a nice space into which you can map this from the real, like Rn?
Well, yeah, you would basically, but you're mapping it back to Rn. You're just saying that stretch every coordinate by root d. It's saying that.
So I'm kind of confused that why, when we are actually, so the d root d is actually essentially just sending it somewhere else and bringing it back, right?
No. Where? No. It's this, right? If you look at the denominator, you want to express the denominator as a norm. There is a space where this is a norm. That space is when you scale every coordinate by root d, then it becomes a norm. Then it becomes a Euclidean norm, or it becomes the Euclidean norm of that space. So it is not that you're scaling it and then you're coming back. You're actually scaling it and you're sitting in the scaled space.
I see.
So it's actually a little bit more complicated. Okay, so I will... yeah, so it's right. So you're sitting in the scaled space,
Yeah.
Which is in some sense distinct from being in the original space. Now, in the scaled space, it turns out to exactly be an eigenvalue. It is not an eigenvalue of the eigenvector of the original Laplacian. But when you scale it, then you get an eigen. There's a correspondence between eigenvectors of one are sort of scaled eigenvectors of the other. But it's,
I've never seen this discussed anywhere in this form, so...
Yeah, no, I agree. So that's what I was poring over this for the past couple of days to really see where is this root d emerging, at least from this perspective. Like you can say why the root d is a scaling, and somehow it is like the correct scaling at which all of these things become eigenvalue problems. Okay, so I close to being out of time. So there's one more thing that I wanted to mention. This has a name. Of course, it's a second eigenvalue. This is also referred to as the spectral gap. And it's a spectral gap because it is the gap between lambda 1 and lambda 2. Lambda 1 is 0. Lambda 2 is, so therefore lambda 2 is the spectral gap. Often, the reason why this is called, okay, so maybe I should say a little bit more about this, which is that n is I minus d to the minus half a d to the minus half. This is the normalized Laplacian. And so sometimes you can look at this matrix instead. If you look at this matrix instead, and this matrix, I don't know, let me refer to this matrix as M. So then you have n normalized being I minus m. And so then the eigenvalues of m, basically if you look at the eigenvalues of m, then they will look like it's essentially the same thing, it's just 1 minus those. Right? Basically because all vectors are eigenvectors of the identity matrix with an eigenvalue of 1. And so if you take any eigenvector of n, you end up with an eigenvector of m, and the eigenvalues of m are going to be 1 minus lambda 1 greater than or equal to 1 minus lambda 2, 1 minus lambda n, and this is of course just 1. And so sometimes you'll see lambda, maybe I've sort of abused notation here, lambda is actually referred to as this, and this is then called the spectral gap. But it's the same whichever way you look at it. Often a lot of these discussions are done when D is regular, the graph is regular, in which case D is essentially just the identity matrix multiplied by something, in which case all the math becomes a lot easier. And everything becomes a lot more easy to deal with when the graph is regular. You don't even actually have to do the normalization in this way. The normalized Laplacian and the original Laplacian are basically just the same thing up to a very simple sort of change. But this matrix M is quite interesting, because if you look at, if you do M to the L times some vector x, so that's d to the minus half a d to the minus half to the power L times some vector x. If you write this out, what you get is you get a d inverse a d inverse so on and so forth, where a will appear L times d to the minus half times x. So ignoring just the beginning and the front, you see that you start getting d to the minus a, d to the minus a, d inverse a, d inverse a. Right? So you can write this as ignoring the first two parts. So you can write this something as like d to the half d inverse a to the power L times d inverse x. So this matrix here is the random walk matrix. That is, if you were to do random walks on the graph, then you end up with this matrix. And therefore, the behavior of a random walk is intimately connected. This is doing a random walk of length L. The behavior of the random walk is intimately connected with the behavior of M to the L times x. But that's basically because the eigenvalues are just like 1 minus those. You're looking at the eigenvalues of the normalized Laplacian. So the normalized Laplacian tells you more about the behavior of the random walk than the normal Laplacian, the unnormalized Laplacian. And that's why the normalized Laplacian is the matrix that you need to understand when you're doing lots of problems related to random walks, related to graph partitioning. Although the connections come, in this way. So anyway, I'm over time now. The main point of today, which is to sort of walk you through this entire relaxation, a fairly complex relaxation, but what this gives is this very beautiful formulation of the relaxation as an eigenvalue problem. And you can see that the second eigenvalue of the normalized Laplacian is a lower bound on the sparsity, on the conductance. And this gives a lower bound. What we will then show is Cheeger's inequality in the next lecture, where we get an upper bound, which is square root of this quantity. So there is a gap, and both are known to be tight, and that is known to be Cheeger's inequality, which relates the sparsity, which is actually a hard quantity to compute, to the eigenvalue, which can be computed in polynomial time. Okay, so with that I'll end, and I'll take any questions that you have.